Hello students, in this video I'll be going over the week 7 content, which is about the normal distribution. I'm going to be talking about probability distributions that are continuous. Remember that last week we talked about discrete distributions. Discrete distributions meaning distributions that deal with a discrete variable that have very specific countable values. A continuous variable, as you could probably guess, is a variable that has continuous values that could be subdivided. All right, let's jump right into it. And the guiding question that I want you to think about while we're talking about this session is, what does it mean to be normal? The normal curve is the curve that we're going to be talking about. But first, let's talk about what a continuous random variable is. It's a random variable where the data can take infinitely many values. If I asked you how many siblings you had, it would be a discrete random variable because you would have either 1 or 2 or 3. It's a value that can't be subdivided. However, a continuous random variable can take infinitely many values. So for, as an example that's here, time at which the U.S. Postal Service delivers a box. If you're expecting a package from the USPS and you're sitting around waiting for it, it could come at, any time, day or night. It could come at 12 noon, could come at 12 midnight, and any time in between. It could come at the exact minute. It could come at 30 seconds past the minute. It could come at 25 seconds past the minute. So that value of exact time that it's delivered could assume many, many, many different values. There are an infinite number of values between the beginning and the end. That's why we call this a continuous random variable. If I were looking at a continuous random variable's probability distribution, I wouldn't use a table. Remember that we use a table here, like the one shown, to represent discrete random variables because the values of a discrete random variable have to be specific values. For example, number of siblings, you could have 0 siblings, 1, 2, 3, or etc. You can't do that with continuous random variables because you would need infinite rows on your table. That's impossible because nobody's ever drawn a table that has infinite rows. You would have to use something else. That's why we use graphs. A graph could represent all the different values for a continuous random variable. This could be 0, this could be 100, and this could be all the values in between. If you needed to find 50.758, it would have to be somewhere on this line. It's easy to do on a graph, but it's very difficult to do on a table. That's why we use a graph to graph continuous random variables. You can see that with a discrete random variable, it has these individual columns. It's kind of like a histogram, right? Because it takes specific values. Whereas a continuous random variable, it could be any value in between. Here's an example just by looking at the values of the continuous random variable. Suppose USPS is going to deliver a package to your front door sometime between 10 o'clock in the morning and 11 o'clock in the morning. It could come exactly at 10 a.m. That would be x equals 0. It's the number of minutes after 10 a.m. where the delivery takes place. It could take place at 11 a.m., which means x is equal to 60 minutes after 10 a.m., right? 10:31 would be 31 minutes after 10 o'clock. That would mean x is equal to 31. It could also be 10:31 and 30 seconds. That means the variable would be 31.5 because it's 31 and a half minutes, 30 seconds, right, after 10 o'clock. So you can see that this variable could take infinitely many values in between 0 and 60, right? So now we've talked about the individual values of the continuous random variable. Now let's talk about how we would describe it in a distribution. A probability distribution, remember, is all of the different possible outcomes of a probability experiment and the probabilities of those outcomes. Remember, it's going to be very difficult to do a table for this situation for continuous random variables, so we're going to be using a graph. Let's try to draw the graph. Here's how we write it out. This is saying x is a random variable. It follows a uniform distribution between 0 and 60. A uniform distribution just says there's an equal probability of any of these values coming up. There's an equal probability that the postal delivery worker rings your bell at 10 o'clock in the morning, or rings your bell at 10:31 and 30 seconds, or rings your bell at 11 o'clock in the morning. It's an equally likely probability. That means it's a uniform distribution. This is what it looks like. All of the different probabilities are exactly the same for all the different times. For example, I gave this example here. What if the person shows up at 10:42 a.m.? Well, that's represented here. That would be 42. X is equal to 42. The probability of that event would be found by just tracing up to this line here. The probability of that event is 1 out of 60. which should make sense to you because you have a 1 out of 60 chance of coming at the 41st minute or the 42nd minute or the 60th minute or the 1st minute, because all of these events are equally likely. Here's another reason why that's the case. I know that this is a shape that I'm very familiar with. This is a rectangle. And a rectangle has the case, or has the formula, that length times width is equal to its area. I know the area under this curve, the area under this graph here, is going to be 1. It should make sense to you because the area is 1, because all of the different probabilities of a certain event, of the probabilities of the different outcomes of a different event, I should say, add up to 1, right? If I'm thinking about flipping a coin, the probability of getting heads is 1 out of 2, the probability of getting tails is 1 out of 2, add those together, you get 1. If you're rolling a die, it's either 1, 2, 3, 4, 5, or 6. All of those probabilities are 1/6 respectively. If you add all those probabilities together, you get 1. So it should be proof to you that all of these probabilities, the area under the curve here, should be equal to 1. Well, if the area under the curve is equal to 1, and we know that this width here is 60, because all the different values of the random variable could be between 0 and 60, that means this has to be 1 divided by 60, because this times this has to give you 1. So it's the multiplicative inverse of the different values of the random variable. Moving on. We just talked about area under the graph briefly, and as I said previously, the area under the curve, under the graph, whatever you want to call it, is always 1. That's representative of the fact that when we're drawing a probability distribution, we're trying to capture all the different possible outcomes, and all of those outcomes is probability. I don't know if outcomes is a word, but here we are. The maximum height of the curve must be greater than or equal to 0 and less than or equal to 1, because the probability of any individual outcome can't be more than 100%, can't be more than 1, and it can't be less than 0. It can't be less than 0%, because if it was less than 0, it wouldn't be a probability, it doesn't count. And if it's more than 1, that means it's more than certain to happen. And you can't have more than certainty, you can only have 100%. All the points must be above the x-axis. If we go back to this graph here, you can see that all of these points are above the x-axis. They're at 1/60, which is in between 0, which is down here, and 1, which would be all the way up here. Moving on through here, the probability of one single outcome is going to be very small. Obviously, if you're thinking about the probability of one single outcome for continuous random variables, it would be very difficult to calculate that. Usually what we do is calculate the probability of a range of outcomes. I don't know the probability of the package coming exactly at a certain time, but the probability of the package coming between this time and this time, it's easier to calculate. And finally, this is the area equals length times width that I was talking about. You probably learned this when you just came out of the womb there, so you probably know all about that. Here's the example that we talk about for uniform probability distribution. We're looking for the probability that the package arrives between 10:15 and 10:30 a.m. So what we can do is say, I know that x is equal to 15 is here, x is equal to 30 is here on the graph, and the distance from here to here is 15, 30 minus 15. Now I need to find the area under the curve between here and here. Luckily for me, I know that this part is 15, this length, and the width here is going to be 1/60, because in a uniform probability distribution, all of the heights of the curve are exactly the same. It's all 1 out of 60. So 1 out of 60 times 15 gives us 0.25. After I'm done, I can check my work. I know that the area under the curve between 15 and 30 is 0.25. That's between 0 and 1, so that is a valid probability. Perfect. Let's now talk about a different type of distribution. We just talked about uniform distributions. Now let's talk about a so-called normal distribution. I'm going to motivate that like this. If you bring your 2-year-olds to the pediatrician and they say, well, they're 33 inches tall. The question is my son's height normal? So the only way that you could try to figure out whether your son's height is normal is look at other people that fit his same criteria, other 2-year-old boys. So in a random sample of 52-year-old boys from this pediatrician, here's the data. And here's your 2-year-old right here, 33 inches tall. Looking at this data is difficult. This is called raw data. Most of the time we can't make any conclusions or draw any reasonable conclusions from just looking at raw data. So what we're going to do is we're going to try to graph it. You know what this graph is. This is a histogram. A histogram organizes big groups of data, big groups of raw data into classes or groups. And then it says, well, for example, these are all the kids from 31.5 to 32.5. These are all the kids from 32.5 to 33.5. And on the vertical axis, the y-axis, it's sometimes the frequency, sometimes the relative frequency, and sometimes the percent. They're basically the same concept. Here's one piece of information that I can glean from this. I can say that more students, not students, I guess these are 2-year-old males, right? More 2-year-old males lie within the restriction of 35 to 36 or 35.5 to 36.5 than any other group. This is the peak. So I might say all of these children are, I don't know, normal, and all of these children are less than normal, and all of these children are greater than normal. This has another meaning in mathematics. This is also the average, right? We call the average height of the 2-year-old males. If we were to take all those numbers on the previous slide, add them all together and divide by 50, we would probably get a number that's very close to 36. All right. Now let's take a look at the interpretations. One of the interpretations is something that we spoke about just before. We observed that the average height is about 36 inches tall. That's the peak here. Another thing that we were able to figure out is that 6% of 2-year-old males were between 32 and 33, or 32.5 and 33.5 inches tall. Why is that important? Because, remember at the beginning of the problem, the child measured to be 33 inches tall. So the child is in the same class, or the same group, as about 6% of 2-year-old males. So that's some important information. So you could go back to the parent that's asking that and says, well, only about 6% of children are that tall. So are they normal? And I guess that's anybody's guess at this point. One thing that I want you to notice is that the histogram itself follows this curved pattern. This curved pattern happens all the time in all sorts of data sets. Data sets from nature, data sets from economics, data sets from grades of classes. All sorts of different data sets follow this pattern. And it makes sense because this pattern is very natural. It represents the fact that if you have a thing that you're measuring, a characteristic that you're measuring, most of those things that you're measuring are going to be around the average. And as you get farther and farther away from that measurement, that's going to happen more and more rarely. It's going to be very rare to see a child that's down here at 40 inches tall. It's going to be very rare to see a child that's down here at about 29 inches tall, right? You should not expect to see those children as often as you see these children. The distance away from the mean is going to represent how much rarer it is. Another thing that measures how rare it is by looking at the percentage. You could interpret it like this. About 12% of children are between 33.5 and 34.5, meaning maybe that there's a 12% chance that the child is going to be between 33.5 and 34.5. There are a number of different ways to interpret it. And I want to show you a couple of different patterns that show the same thing. Here's one such pattern. Here's an example of a normal curve. This is the number of years worked in a cereal factory. It looks like for 11 years worked, 200 employees are in that group. So in other words, there are 200 employees at this cereal factory that have worked for 11 years. There are only 11 employees that have worked for 20 years, and there are only 15 employees that have worked for 1 year. This pattern, as you can see, is that same classic curved pattern. It's a normal curve pattern. So it comes up in all sorts of different walks of life. Another example is the probability of heads flipped on 16 coin tosses. Obviously, it's very likely that when you flip 16 coins, you will get 8 heads because that's half of the results, right? 8 heads, 8 tails. But it's certainly possible to get 7 heads and 9 tails. And it's also possible to get 6 heads and 10 tails, right? But the probability of getting those weirder results gets lower and lower. And I want you to think about the height of these bars as probability. As the height of the bar gets lower, the probability of that outcome becomes lower. That's how I want you to interpret this, because the area under the curve is probability, and the height at a specific value is going to represent the probability of that value. Great. Hopefully that makes sense. Moving on, here's another example. The weights of newborn babies at a hospital. If you just got born at a hospital and you just got weighed, it's very likely that you'll be in between 3 and 4 kilograms. It's very unlikely that you'd be up here at between 5 and 6 kilograms. And you see there's a little bulge here. This is for premature babies that would be, kept in the NICU for a little while. But most of the babies fit this normal curve very, very nicely. Another example here is number of goals scored by hockey teams over an 82-game season. There are some powerhouse teams that are able to score between 75 and 80 goals over the 82-game season, which is fairly rare when you talk about hockey teams. It's more likely that they will score the average, which is between 40 and 45 goals. In fact, 2,482 teams have met that criteria over the course of hockey history. Another normal curve. Look at this. This is SAT scores recorded in 2010. You would say that this is a very normal curve with an average that you can pretty easily figure out. And you can easily turn these frequencies into percentages. Like instead of saying this is 19,000, you could say 19,000 divided by the total number of kids that took the test, and you would be able to get the relative frequency and change that into a percentage. Another more silly normal curve example is the heights of 3,000 adult English male criminals around 1900. It should make sense to you that there are some extremely tall criminals, there are some extremely short criminals, but most criminals are about average height. Between 5 and 6 feet tall. So I just wanted to show you all of those to represent the fact that normal curves are all over the place. This is something that comes up in all walks of life. The age at retirement of Major League Baseball players from 2006 to 2016. Some retired very early, maybe due to injury or something like that. Some were able to play the game way past their prime. I think that Curt Schilling was one example of that. That's a player that played for a very long time. Barry Bonds was another. But most players retire when they're 33 years of age, which is a pretty good time to retire because you get to, enjoy your earnings throughout the rest of your adult life. Here's another example. Listen, I could belabor this point, but the idea is every walk of life, every field, you're going to find normal curves in it. The reason that we're using the word normal for this is because it just happens so often. It happens in all sorts of different pursuits. So now we have this idea of normal curves. Let's see how we can work with it. First, let's talk about the characteristics of a normal distribution. The mean is in the middle. We call that the center of the normal distribution. It's the mean. It's equal to the median for a perfect normal distribution. Most things in life aren't perfect. So most things can be modeled by a normal distribution, but they're not exact. So the median and the mean with real life data might not be exactly the same, but for a perfect normal distribution, an ideal normal distribution, mean and median are the same. Symmetric, which means that one side looks the same as the other side. The tail to the left should look the same as the tail to the right, which means half of the area lies below the mean, half of the area lies above the mean. Asymptotic is an Algebra 2 word, which means it approaches without ever reaching the value. They're asymptotic to the x-axis. They're asymptotic to y equals 0, which means they get very close to y equals 0, but they never touch that x-axis. And they have two inflection points. This is a word that you will need to know if you go into a stat class, either AP Stat or stat class in your college. But inflection points are one standard deviation above and one standard deviation below the mean. Speaking of inflection points, here's one and here's one. One standard deviation above, or the mean plus the standard deviation, and one standard deviation below, the mean minus the standard deviation. So what we're dealing with here is something called the empirical rule, which says 68% of the data lies within one standard deviation of the mean. That is a mathematical fact that if it follows a perfect normal distribution, 34% of the data lies below the mean and between one standard deviation, and 34% of the data lies above the mean between one standard deviation. 34 and 34 is 68. We also know that 95% of the data lies within two standard deviations, so in order to get this 13.5, we took 68, subtracted it from 95, and cut it in half. That means 27% lies within this part and also this part. 27 cut in half is 13.5. We did the same calculation to get the 2.35. I will leave it to you. It is a simple numerical procedure. You just got to cut it in half. All right, so the empirical rule always works, so we can answer questions using the empirical rule like this question. Mr. Lowe's physical education class records the weight in pounds of all students at Queens Metropolitan High School, and it follows a normal distribution, as you could probably expect. The mean is the peak, the middle, that's 140, easy question. The standard deviation is based on these, this inflection point here and this inflection point here, 120 and 160. That's 20 below and 20 above the mean, which means the standard deviation is going to be 20. And it says approximately what percent of students weigh between 100 and 140 pounds. I'm just going to use the empirical rule. I know that 34 and 34 go here and here. I know that 13 and a half and 13 and a half go here and here. So I can say between 100, which is here, and 140, which is here, I can add 34% and 13.5% to get 47.5%. Easy question. There are two different interpretations for area under the normal curve, and we're going to be using both of them in this presentation. The proportion of individuals within the population with that characteristic or measurement. So I could say I'm looking at all of the different possible, let's say, people in Queens Metropolitan High School for the previous example. And if I'm looking for the people with that characteristic that falls within that interval of values, that interpretation is 47.5% of students weigh between 100 and 140 pounds. That's one interpretation. The other interpretation is probability. So we can take it like this. The probability that a randomly selected individual has that certain characteristic or measurement, I could say there's a 47.5% chance that a randomly selected student from Queens Metro will weigh between here and here. So the two interpretations are 47.5% of students actually are in that zone, or there is a 47.5% chance that if I randomly select a student, they will lie within that zone. Those are the two different interpretations. Let's take a look at them in action. The weights of giraffes are approximately normally distributed. I would love to have been the researcher that was tasked with weighing all of these giraffes. Here, go stand over there on that scale. The mean is 2200, which is here. And the standard deviation is 200, which means here's the first inflection point below, here's the first inflection point above. I've drawn this normal curve, and you should be able to do that by just writing the mean here, and then subtracting the standard deviation a couple of times, and then adding the standard deviation a couple of times in order to get the curve. Easy. It's asking us to shade the area under the normal curve to the left of 2,100 pounds. Here's 2,100 pounds right here, and it's shaded in blue, or I guess that's lavender, some kind of purplish or bluish tint. And it says, suppose the area under the normal curve from here to here is 0.3085. The two interpretations that we just talked about are these. The proportion of giraffes whose weight is less than 2,100 pounds, that's 0.3085. So they're 30.85% of giraffes weigh less than 2,100 pounds. Or we could say the probability that a randomly selected giraffe weighs more than 2,100 pounds, well, that should say less than, sorry, it should say less than, is 0.3085. There are two different interpretations based on either proportion or probability. All right, now let's move on to talking about a so-called standard normal distribution. We looked at a normal distribution before with its mean and its standard deviation that are whatever numbers it wants to be. What I could do is take any normal curve and standardize it. In other words, I'm going to turn the mean into 0. And I'm going to take each standard deviation and just turn them into 1. That standardization process means I'm able to compare any normally distributed variable with each other. Fantastic. I can compare how abnormal a giraffe is from other giraffes. I can compare how abnormal a baby's height is from other babies' heights. I can compare how old a baseball player retires as compared to other retirement ages and see how weird it is, how abnormal it is. And I'm doing that using the z-score formula. The z-score formula is very easy. The z-score is the converted score. It's going to be between, positive infinity and negative infinity, but most of the time it's between 3 and negative 3. And to use the z-score formula, I'm going to take x, which is the observation that I'm thinking about. I'm going to subtract the mean from it, and the mean is always going to be the same for a normal distribution, for a given normal distribution. And I'm going to divide that by the standard deviation. Once I do that calculation, I get a standardized value, and that value should answer the question, how weird is your observation? I think we did an example before with Kevin Garnett. We were able to figure out how weird his height was as compared to other basketball players. Answer, pretty weird. Here's an example of standard normal distribution. I can take that giraffe graph, oh, that's nice to cite, giraffe graph, that we talked about before, and standardize this curve. Instead of calling this mean 2200, I can call it 0, and the conversion factor is very easy. 2200, which is the observation I'm talking about, minus the mean, which is 2200, that's 0. I divide it by the standard deviation, which is 200. Well, 0 divided by 200 is just 0. I can do the same thing here for 2400. 2400, which is my observation, minus 2200, that's 200. 200 divided by 200, which is the standard deviation, that's 1. I can do the same thing here. 1800 minus the mean, which is 2200, that's negative 400. Negative 400 divided by the standard deviation, which is 200, that's negative 2. Easy peasy. The question asks us to convert 2000 and 2300 to normal z-scores. That's here and here. It's not difficult to do. You do one subtraction, one division. Bob's your uncle. All right. It's fun to use the calculator. Everyone agrees. I think that in a recent poll, 100% of students agreed. The calculator can find the area under a normal curve very, very easily. Here's how they do it. You draw the normal curve and you label the mean and the standard deviation, kind of like this. And then what you can do is shade the desired area. In this case, we shaded the area between 2000 and 2300. And then what we can do is use the normal CDF function. When I'm trying to find normal CDF, I press second, which is this button. I press vars, which is this button. And then I go to where it says normal CDF, which is the second one on my TI-83 Plus, which is a dinosaur of a calculator. Once you get there, you're going to put in 4 different arguments or 4 different values: the lower bound, the upper bound, the mean of the distribution, and the standard deviation of the distribution. Once you put in those 4 values, you will get the area under the normal curve, which can also be interpreted as the probability of getting the value that's between this lower bound and this upper bound. You want an example? Good, because I got one here. What's the probability that a randomly selected giraffe weighs between 2,000 and 2,300 pounds? Well, the lower bound is 2,000, the upper bound is 2,300, the mean is 2,200, that's what it says here, and the standard deviation is 200, that's what it says here. Normal CDF has the lower bound first, the upper bound 2,300 second, the mean third, and the standard deviation fourth. That means that there is a 53.28% chance that a randomly selected giraffe is going to be between 2,000 and 2,300 pounds. Pretty good. It also means, if you want to do the interpretation of proportions, that 53.28% of giraffes that currently exist lie between 2,000 and 2,300 pounds, respectively. You should know that if I standardize the curve, it's going to give me the same answer. I'll prove it to you. The z-score for 2,000 was -1. The z-score for 2,300 is 0.5. And when I'm doing normal CDF with a standard normal curve, the only thing I have to do is put in the z-scores for the lower bound and upper bound. And I use 0 and 1 for the mean and the standard deviation, because in a standard normal curve, the mean is always 0. Standard deviation is always 1. It's a fun little song that I just wrote. And you should see I got the same exact percentage. There are 3 different situations that you're going to encounter in this class. Situation number 1, I might say, here's a value. I would like you to find the probability that the characteristic of a randomly selected individual is less than that value. If we're talking about less than that value, we need to identify this value because we need a lower bound. Remember that when you're entering lower bounds into the calculator, you usually use a number, but there's no number here because this keeps on going forever and ever and ever and ever and ever and ever and never reaches the x-axis. So I can't use the symbol infinity in the calculator because if I look back at the calculator, there's no symbol for infinity here. So what I'm going to do is I'm going to use the next best thing. Where was I? I think I was... Oh my gosh, where was I? I'm lost. Is it here? No. Aha, it's here. I can't use negative infinity in my calculator. So I'm going to use the next best thing. I'm going to type in -10 to the 99th power. That's not at negative infinity, but it is a very, very, very negative number. It's so negative a number that it's the most negative number that the calculator can think about, -10 to the 99th. So I'm going to use that as my lower bound if I can't use negative infinity. The other situation, or one other situation that I could put you in, is here's a value. I want you to find the probability that the characteristic of a randomly selected individual is greater than a certain value. Well, in this case, I would use my upper bound as positive infinity, but again, there's no infinity button. So instead of using positive infinity, I'm going to use positive, you guessed it, 10 to the 99th. That would mean that I don't have a number that I can put in my calculator that's infinity, but I'm going to put just a very, very severely large number, which should be good enough. For situation 3, I don't have to worry about that 10 to the 99th thing because all I'm dealing with is one value here as the lower bound, one value here as the upper bound. Let's see it in action. For less than, we're using the lower bound, which is negative infinity. But you know we can't put negative infinity in the calculator, so that's why I put negative 10 to the 99th here. The upper bound is 99.2. The mean is 100 and the standard deviation is 0.45. That's based on this problem. If I'm looking at the length of a certain type of steel rod being a normal distribution with a mean of 100, that's where this came from, and a standard deviation 0.45, that's where this came from. We're looking for the probability that a randomly selected steel rod has a length that is less than 99.2. So here's my 99.2, that's my upper bound. My lower bound, as I said before, is negative infinity. Plug it into the calculator, use normal CDF, bada bing, bada boom. The second situation, remember, was greater than. So here's a situation where the combined GRE score is normally distributed. The mean, which is right here in the middle, is 1049. Standard deviation is 189. So I'm using 1049 and 189 as my mean and standard deviation. Columbia wants a minimum score of 1200, which means 1200 is going to be here. And a minimum score means either 1200 or greater. So I would use my lower bound as 1200 and my upper bound as positive infinity, but I can't put positive infinity into my calculator, so I must use 10 to the 99th, positive 10 to the 99th. I get a probability. It's super easy. Just use the calculator. Here's between. Remember, I don't have to worry about infinities if I'm dealing with between. The cell phone manufacturer makes batteries with a mean charge of 3.7 volts and a standard deviation of 0.15 volts. I want to figure out the percentage or the proportion of manufactured batteries between 3.5 and 4. So 3.5 is my lower bound, 4 is my upper bound. My mean and standard deviation are what they are. And normal CDF tells me 88.60% of batteries are going to be effective. Another type of question is finding a z-score for a given area. So for example, I have 25% of my area, or 0.25, here. I want to know what this z-score is, what this z-value is. In order to figure this out, we need to use not normal CDF, but inv-norm, the inverse of normal. So what we're going to be doing, well, there's another option. You could use this table, but let me tell you, let's not use this table. The table is difficult to use. It requires you to do a lot of estimating. And remember we said the area was 25, 0.25? That doesn't really exist on this table. This value I'm using is because it's the closest one to 0.25. This one's farther away, this one's farther away. And in order to figure out the z-score, now I have to look up here and down here and add those two things together. Negative 0.67. I guess that's not really adding, that's combining, but whatever. So using this table, I'm estimating negative 0.67. But there are a couple of different reasons why we don't want to do this. Number one, I don't want you to use this table. It's dumb. Number two, 0.67, negative 0.67 rather, is an estimation. What I want is an exact answer. So the calculator is going to give me that exact answer. I have 0.25, which is the area under the curve. And what I'm going to do is going to go to second vars, the same thing I did before. And now I'm going to go to inv-norm. Inv-norm is the inverse of normal. So the calculator accepts three different arguments. 0.25 is the area. 0 is the mean. 1 is the standard deviation for a standard normal curve. And using that, we'll find the z-score. Remember, negative 0.67 from the approximation from the table. This is a much better value. It's much more accurate. There are a couple more examples of doing that here. I encourage you to look through this yourself. Finding the actual z value is not that difficult because all we're using is the inv-norm feature. This one is a little bit strange because it says the area to the right of the z-score is 0.4021. I can't find values to the right of the z-score. I can only find values to the left of the z-score. So I have to use this area instead. The entire area under here is 1. So if this part is 0.4021, this part is the complement of that, which is 0.5979. I subtracted it from 1. And then last but not least, I'm asked to find the z-scores between which 92% of the area lies. So the z-score between here and here, or the percentage between here and here is 92%, which means 8% is left over, 4% down here, 4% up here. So now I need to find the z-score for 0.04, which is 4%, which is negative 1.7507. It's symmetrical, so this is going to be the same exact value except positive. Beautiful. Rounding this out, there are a couple of different exercises. I encourage you, again, to take a look at these exercises on your own. This is fairly straightforward to figure out. I know that the probability that x is less than 3, x is greater than 3, that's what this says, is the probability that the value lies between 3, which is here, and 10 to the 99th, which is up here. It is positive infinity, but I just can't put positive infinity into the calculator. So I get this percentage, which I'm rounding to 4 decimal places, which is usually good for any statistical means or any, even trig, you take 4 decimal places. For IQ scores, they're normally distributed with a mean of 100 and standard deviation of 15. The 45th percentile means the value below which 45% of the observations lie. So I'm looking for this value. If I'm looking for a value, I use inv norm. 45% or 0.45 goes here. That goes here. The mean is 100. The standard deviation is 15. It doesn't get any easier than that. And we'll round out this lesson with a question about bass. You know that, obviously everybody knows that the minimum legal length for black sea bass is 12.5 inches, which means if it's below 12.5 inches, we got to throw it back into the ocean. If the mean length of a black sea bass is 11.2 inches, that's here. The population is normally distributed. I drew that here. And the standard deviation is 1.8 inches, which I represented by adding 1.8 3 times and subtracting 1.8 3 times. We're looking for the percent of black sea bass. Percent, I'm using normal CDF. 12.5 is my lower bound. Upper bound, 10 to the 99th, that's up here. 11.2, that's my mean. 1.8, that's my standard deviation. 0.2351, that means that 23.51% of sea bass can be kept, and the other 3/4 of sea bass got to get tossed back into the ocean. All right, this was the week 7 notes. We talked about normal distributions, continuous random variables, the uniform distribution, although we didn't talk too much about that because not much more needed to be said, and we talked about how to work with area under the curve as it pertains to probability and proportions of the population. All right, students, good luck studying.